Hello everyone and welcome back to the Frame Channel. Friction is the invisible and unavoidable force present in all processes which involve contact and movement between two surfaces. Friction generates heat as it tends to work against productive movement. While countless advances to reduce the losses and heat of friction are a strong focus in mechanical engineering, friction cannot altogether be avoided. However, friction can be harnessed to create heat with mechanical movement without the use of additional fuel. Friction welding is one industrial process that harnesses and uses the heat produced during friction. It takes advantage of the natural heating of objects in motion and exploits it to an industrial scale. The intense friction technology fuses metal parts in seconds. It uses only friction to convert mechanical energy into the heat power needed to weld solid metal. Oddly enough, friction welding is as much defined for what it lacks as what this extreme process involves. How did friction welding get this far? Is friction welding the best process to use in manufacturing today? Electrical arc welding became the best available welding technology through most of the 20th century, providing further weld reliability. It was not until the 1960s when a manufacturing process was developed into what we know to be friction welding today. Friction welding is one of the most contemporary welding developments of the current era. Unlike fusion welding, where melting and rapid solidification occurs, welding with friction does not melt the metal. In fact, friction welding is a solid-state process where intense heat plasticizes the material, which often glows red-hot under intense pressure. The material then re-hardens as it cools, forming an exceptionally strong bond, all without melting the working metal. Friction welding only requires two components for success. Relative motion of the mandrel surface to another is needed. Second, mechanical pressure is required to force the welding surfaces together. Extreme heat is generated when the interface between the two surfaces is rotated or scrubbed together under the pressure of hundreds of tons of force. The relative rotating or scrubbing motion is known as the kinetic force, while the mechanical pressure squeezing the work together is known as the forging force. Kinetic energy input into friction welding machines is driven by powerful electric motors or hydraulic actuators. Applications that necessitate the use of friction welding either require a very strong and homogeneous weld bond, high manufacturing repeatability, weight savings, or a combination of all three. Since friction welds use no consumable weld material, mass-produced welds can be cheaper and quicker to produce. Several variations in friction welding have been developed, which provide individual advantages for different part geometries. Rotary friction welding will be used when at least one of the parts can be rotated about a symmetrical axis. The relative motion for heat creation is by rotation. 400 to 1500 RPM causes intense frictional heat for rotary friction welding. Shafts, spindles, or rings are often friction welded with rotary friction welding. Linear friction welding is mostly useful for parts with non-symmetrical or complex part geometry. The relative motion creating heat is caused by a back-and-forth oscillation or scrubbing motion. In the case of linear friction welding, oscillations of 100 to 240 Hz are typical. Friction stir welding is a specialized friction welding process that employs the same principles as other variations of friction welding, but allows for both fused parts to remain stationary. by the use of a non-consumable pin tool, which is plunged into the interface and forced through the material. The material is heated to a plastic condition, and the interface is mixed mechanically. Then, as the tool passes through the interface, the wake is cooled to produce a strong, smooth, forged joint. Applications for friction welding vary in nature. The needs of manufacturing near the extreme limits of material strength often advantage the use of friction welding. Friction welding may be seen in turbochargers, spindles, welding of dissimilar electrodes, automotive parts assembly, or in turbine and compressor blades. The incredible versatility of friction welding is known in the manufacturing industry, even in the field of rocket science. For instance, NASA's famous rocket engine, the RS-25, was built by California-based company Aerojet Rocketdyne. A total of 16 of these rocket engines have been built so far by this aerospace company, which is worth over $4 billion. In 2016, a crucial friction welding application was proposed to construct the new RS-25 rocket engines. Friction welding, commissioned by the friction welding specialists at Manufacturing Technology, Inc., MTI, provided a fast and reliable process for components of the rocket engines. During 4 days of operational friction welding, the MTI's upgrades made more than 600 welds that led to the completion of the RS-25 booster engine, ahead of schedule. It is one of the newest welding techniques available, providing advantages in the manufacture of the specific need of the end product. Friction welding is known to benefit processes with large, bulky geometry, extreme strength requirements, dissimilar metals, or the need for high heat tolerance. Friction welding harnesses the natural friction force, requires no consumable weld stock, produces a strong weld, and does it all without melting metal. With no harmful arc glare, no fumes, no smoke, and no radiations, this intense friction welding technology is gaining ground across the globe. That's the end of this feature on the Frame channel. I hope you enjoyed it. Make sure to subscribe to this channel to catch us on our next video. See you next time.